This will be an explanation of the mathematical framework for uniform acceleration. Pretty much for this entire semester, we're going to focus only on the two basic types of motion. Uniform velocity, which we sometimes call uniform motion. That's characterized by something moving in a straight line at a steady speed. That has only really one equation, which is the velocity, or the average velocity, equals the displacement over the time. I'll come back to that. But uniform acceleration. Once again, we're going to stick with straight line motion for now. We can also have uniform circular motion, which will be a whole other topic about a month from now. But these equations right here in the box apply to straight line uniform acceleration, where something is either speeding up or slowing down steadily. There will be 5 variables or parameters. Different books use different symbols. The symbols that I use are as so there they are: the final velocity v sub f, the initial velocity v sub I of an object that's accelerating. A would be the actual acceleration. The typical units will be meters per second squared. For the velocities, meters per second. S will be the letter we use for displacement, which probably about half the books use. There are other options, but we're going to be using S consistent with our textbook, and T for time. Every problem we do will have this same setup. So these problems, in one sense, once you have them set up, they're very mechanical because you're going to be doing the problems the same way every time. We have 4 equations here. I'm going to run through these 4 equations and show you where they come from, and then we'll practice some problems. This first equation is really just a restatement of the definition of acceleration. If you go back to our notes a week or so ago, our definition for average acceleration, A equals delta V, or change in velocity over time, where change in velocity, or change in anything, is the final value minus the initial value. So V sub f minus V sub I is delta V over t. If you just rearrange this, multiply both sides by t, we'd have A times t equals V sub f minus V sub I. And then just add the V sub I to both sides. You end up with our first equation in uniform acceleration, just a restatement of the definition of acceleration. That would be V sub f equals V sub I plus AT. This second equation, there's nothing magic about the numbering system. I mean, this could be the first equation, the other one could be the second equation. It's just another equation that applies to uniform acceleration. It's really just a reformulation of the definition of average velocity. Once again, our equation for average velocity, V, average velocity, is your displacement over your time. Now, if you think about it, I'm not going to go into a whole lot of detail here, but if something is uniformly accelerating from like 30 meters per second to 50 meters per second over a period of time, its average velocity is 40 meters per second. It's always so the average will simply always be adding the first velocity plus the second velocity divided by 2, just like averaging any two numbers you were given. So if we replace the V average with the mathematical definition of averaging, taking the two velocities and dividing by 2, that would be V sub f. That would be V sub f plus V sub I over 2. That's the averaging. So I replace the V average on the left side of this equation with the mathematical definition of averaging, two numbers, equals S over T. So once again, if you now just rearrange here and using the algebra, this bottom equation just rearranges by, if you cross multiply, you just cross multiply the T, you end up with S equals 1/2 times the quantity Vf plus Vi times the T that we cross multiplied. And then we flipped it around using a symmetric property. This third uniform acceleration equation from the very first page, displacement equals the initial velocity times time plus 1/2 AT squared is simply just a combination of the first two equations I just dealt with on the previous 2 pages, the two definitions, the definitions of average acceleration and average velocity. If you combine those two equations, you get this equation. And here's how that works. I'll write those two equations down. So here are the first two equations from the definitions, and I've highlighted in blue what I am going to substitute. I'm going to substitute all of this, that's v sub I plus at, over into equation number 2. So on the right over here I have equation number 1, which is v sub f, final velocity equals initial velocity plus at. Substituting that in to the first equation, which results in this. 1/2 times the quantity v sub I plus at plus the v sub I closed quantity times t. Now this looks like a lot of algebra, but it's combining like terms. Inside the parentheses we have the two v sub i's, so v sub I plus v sub I is 2 v sub I. And then if I distribute the 1/2 and the t, you can see that I end up with what I have at the top of the page here. So I'll do it in 2 steps. So I distributed the t through the parentheses, distributive property. T times 2 v sub I is 2 v sub I t plus at squared. I'm going to go to another page now. If I distribute the 1/2, the third equation, that is the third equation, which is s equals, then the 1/2 times the 2 cancels, you get v sub I times t plus 1/2 a t squared. So here's the fourth uniform acceleration equation. Once again, it's a combination of the first 2 equations, which were definitions. What we're trying to establish here is that this is just not made up stuff. This is actually mathematically valid work and equations that can be used to solve physics problems based on the rules of algebra. And this one here is probably going to be the most algebraic, so bear with me here. It is algebra, though. It's not pre-calc, it's not calc, it's not trig, it's not geometry, it's algebra. So here we go. I'm going to write down the first 2 equations. The big picture here is what we're going to do is we'll take the second equation, the v sub f, which is equation number 1 on the very first page. Doesn't really matter which one's number 1, which one's number 2. We have 2 equations here that are definitions, reformulated. We'll take the one on the right here, v sub f equals v sub I plus at. We're going to solve that for t. I'm going to move the v sub I to the left and then divide by a. So you have v sub f minus v sub I equals at. Divide everything by a. In other words, move the a to the left. You end up with v sub f minus v sub I over a equals t. Everything we've been doing on all these pages is just following the rules of algebra and manipulating these equations. What we will do now is we'll take this value for t and substitute it over here in the first equation. And this is going to look quite intimidating, but when you do that you end up with the following. So this is what it looks like once you've subbed in. Now, those of you who are really into algebra, like I am, I enjoy looking at this and trying to figure out how does this simplify. Kind of brings a little warm, fuzzy feeling in my heart. So I'm going to move the a way over to the left, factor that out, and then you'll see some patterns here that might be similar or bring up memories of things from your freshman or sophomore year algebra classes. So here at the bottom of the page is just, once again, moving the a over to the left, and you might recognize something in this new equation. Essentially what you have is the difference of 2 squares factored out. Hopefully that rings a bell. I'll go to the next page and continue. So here we have the equation from the previous page. What we're going to do now is take the two binomials, the v sub f plus v sub I times the v sub f minus v sub I, as the difference of two squares. We're going to multiply them the long way. Some of you may remember the shortcut, but I'm going to do it the long way right now, which, if you remember from algebra class, is to take, like the FOIL method, first, outer, inner, last. In other words, the first two terms will multiply, firsts, then the outers, inners, and then the last ones. It always reminds me of a face. Kind of looks like a face. But if I do that, I end up with the following. I end up with my four products. The v sub f times the v sub f is v sub f squared. And then minus the v sub f times the v sub I plus the v sub f times the v sub I minus the v sub I squared. But what you'll notice in this four-term polynomial now, in the parentheses, the middle two terms are going to cancel. So you end up with the following. And that's always the most rewarding step for me, getting rid of all that garbage in the middle there. And some of you might now see how this is very similar to what we're trying to prove or support. I'm going to move the 2a over to the left-hand side, and then we're really close to our final product. So I've moved the 2a, I've multiplied both sides of the equation by 2a, following the golden rule of algebra. And once again, as I mentioned in class, algebra really only has one rule. All of algebra can be boiled down to one rule, and that is do unto one side of an equation what you do to the other side of the equation. That basically covers over 90% of the algebra you'll ever do. What we're going to do now is simply add the v sub I squared to both sides and then use the symmetric and commutative properties to put this in the same form as the first official listing I have on the very first page for equation number 4 for uniform acceleration. I'll go to the next page. So there it is, by just rearranging the terms and flipping things around from the previous page. That's our fourth equation for uniform acceleration. I'm not going to make you memorize these equations or this process, but you need to be aware of where these equations come from so that you can have confidence that they're valid and useful. We're going to be solving a lot of problems now in the next 2 to 3 weeks directly using these equations, and then for the rest of the year we'll use these sporadically. Now I'm going to give you some example problems on how to use these equations, and it's fairly mechanical. Even if you don't understand how these equations were derived, you need to be able to use these equations, and this is how we're going to use them. So here is a sample question.